When troubleshooting electrical circuits, verifying connections is crucial. This involves inspecting connections in fixtures and at the panel to identify loose or faulty connections that could cause power loss. Identifying shared neutrals is essential to isolate the issue and prevent electrical hazards. Recognizing that multiple circuits may share a neutral conductor is key. Properly torquing the screw connecting the shared neutral ensures a reliable electrical connection and eliminates potential arcing or overheating. Rearranging breakers to ensure that circuit sharing neutrals are adjacent in a panel reduces the likelihood of cross-connection and potential electrical issues. While an electrician may assume that circuits sharing the same conduit were multi-wire circuits, further investigation could confirm the specific neutral sharing arrangement in the wiring system. Testing or tracing the circuits can provide more definitive information. The electrician's logical approach is often used as a starting point for troubleshooting and resolving electrical problems, especially in older buildings where documentation may be limited. In most jurisdictions, electrical codes prohibit the sharing of neutrals between different circuits unless they are specifically designed and protected as multi-wire circuits. Before performing any electrical work, it's imperative to shut off the power at the main breaker to prevent electrical shock or injury. Troubleshooting electrical issues require specialized knowledge and experience. It's always advisable to consult a licensed electrician for any electrical repairs or modifications. When examining electrical panels, the presence of shared neutral wires can lead to several problems if not properly addressed. Firstly, it's important to understand the concept of a multi-wire branch circuit. This type of circuit consists of two or more ungrounded conductors, meaning hot wires, that have a voltage between them and a neutral conductor, with the neutral being common to all conductors. The key is that the multi-wire branch circuit must originate from the same phase, or different phases, of a 240 volts or 208 volts supply. The reason for this configuration is to share the neutral conductor and reduce the amount of wiring required. However, if two separate circuits in the same phase share a neutral, it can lead to an overloaded neutral conductor. The current in the neutral conductor will be the sum of the currents in the two hot wires, potentially exceeding the ampacity of the neutral wire. This can cause overheating, insulation damage, and even a fire hazard. Secondly, an important aspect to remember is that electrical codes generally prohibit the sharing of a neutral conductor by circuits originating from different sources, such as two separate panels or different transformers. This is because the neutral conductor is intended to carry the unbalanced current from a single source. If multiple sources are connected to the same neutral, it can create a path for circulating currents, leading to voltage fluctuations and equipment malfunction. When troubleshooting a situation where lights in receptacles are dead, and you suspect a shared neutral issue, there are several steps you can take. 1. Visually inspect the panel for any signs of loose connections, damaged wires, or overheating. Pay close attention to the neutral bar, where all the neutral conductors are terminated. Look for any discoloration, melting, or other signs of distress. 2. Use a multimeter to measure the voltage between the hot wires and the neutral conductor at each receptacle and light fixture. If the voltage readings are significantly different than the expected 120 volts, it could indicate a problem with the neutral connection. 3. Check the continuity of the neutral conductor between the panel and the affected devices. A lack of continuity indicates a break in the neutral wire, which can cause the devices to stop working. 4. If you suspect that two circuits are sharing a neutral, try disconnecting one of the hot wires at the breaker and see if the other circuit still works. If it does, it confirms that the two circuits are sharing a neutral. 5. Use a clamp meter to measure the current flowing in the neutral conductor. If the current exceeds the ampacity of the neutral wire, it is a clear indication of an overloaded neutral. When you discover shared neutral wiring, there are several ways to correct the situation. Firstly, separate the neutrals of the two circuits and run a dedicated neutral wire for each circuit back to the panel. This is the most straightforward solution and ensures that each circuit has its own neutral path. Secondly, if it is not feasible to run new wires, consider using a multi-wire branch circuit configuration. This involves using a two-pole breaker to supply both circuits with power and connecting the neutral conductor to the neutral bar in the panel. This configuration ensures that the neutral conductor only carries the unbalanced current between the two circuits. Thirdly, ensure that all connections in the panel are clean and tight. Loose connections can cause arcing, which can damage the wires and create a fire hazard. Use a torque screwdriver to tighten the screws to the manufacturer's recommended torque specifications. Finally, always follow proper safety procedures when working with electrical wiring. Turn off the power to the circuit at the breaker before working on any wiring. Wear appropriate personal protective equipment such as gloves and safety glasses. If you are not comfortable working with electrical wiring, consult a qualified electrician. Now let's consider in more detail the importance of properly torquing electrical connections. Torque refers to the rotational force applied when tightening a screw or bolt. In electrical connections, proper torque is essential for ensuring a secure and reliable connection between the conductors and the terminals. When a screw is not tightened enough, the connection may be loose, resulting in increased resistance at the point of contact. This increased resistance generates heat, which can damage the insulation on the wires, melt the terminals, and even cause a fire. On the other hand, over-tightening a screw can also be detrimental. It can strip the threads on the screw or the terminal, damaging the connection and making it difficult to remove the screw in the future. Over-tightening can also deform the conductors, reducing their contact area and increasing resistance. To ensure proper torque, manufacturers provide torque specifications for electrical connections. These specifications indicate the amount of torque that should be applied to the screw to achieve a secure connection without damaging the components. Torque specifications are usually expressed in inch-pounds or Newton-meters. To apply the correct torque, a torque screwdriver or torque wrench is used. These tools are designed to measure and control the amount of torque applied to the screw. They typically have a dial or scale that indicates the torque value, and they will click or slip when the desired torque is reached. When using a torque screwdriver or torque wrench, it is important to follow the manufacturer's instructions carefully. Firstly, select the correct torque value for the connection you are working on. Secondly, set the torque screwdriver or torque wrench to the selected value. Thirdly, position the tool on the screw and apply force until the tool clicks or slips. Do not continue to tighten the screw after the tool has reached the set torque value. Regularly check the calibration of your torque screwdriver or torque wrench to ensure that it is providing accurate readings. Calibration can be performed by a qualified calibration laboratory. In addition to proper torque, it is also important to ensure that the conductors are properly sized for the load they will be carrying. The ampacity of a conductor refers to the maximum amount of current that it can safely carry without overheating. The ampacity of a conductor is determined by its size, material, and insulation type. Electrical codes specify the minimum conductor size required for different types of circuits. For example, a 15 amps branch circuit typically requires a 14 American wire gauge copper conductor, while a 20 amps branch circuit requires a 12 American wire gauge copper conductor. To determine the correct conductor size, consult the National Electrical Code, specifically Table 310.15b16, which provides ampacity ratings for various conductor sizes and insulation types. When selecting conductors, it is also important to consider the voltage drop in the circuit. Voltage drop refers to the decrease in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause lights to dim, motors to run slowly, and electronic devices to malfunction. The amount of voltage drop depends on the length of the conductor, the current flowing through it, and the resistance of the conductor. To minimize voltage drop, use larger conductors, shorten the length of the circuit, and reduce the load on the circuit. Electrical codes specify the maximum allowable voltage drop for different types of circuits. For example, the National Electrical Code recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. To calculate voltage drop, use the following formula: voltage drop equals 2 times the length of the conductor in feet times the current in amps times the resistance of the conductor per foot divided by 1000. The resistance of the conductor per foot can be found in electrical handbooks or online resources. Another important aspect of electrical wiring is grounding. Grounding refers to the connection of electrical equipment and circuits to the earth. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electrical shock. There are two types of grounding: equipment grounding and system grounding. Equipment grounding refers to the connection of non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and motor frames, to the grounding electrode system. System grounding refers to the connection of the neutral conductor of an electrical system to the grounding electrode system. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. When a fault occurs in an electrical system, such as a short circuit between a hot wire and a metal enclosure, the fault current will flow through the equipment grounding conductor back to the source. This high current will quickly trip the circuit breaker or fuse, disconnecting the power and preventing electrical shock. Without proper grounding, the fault current may not be sufficient to trip the breaker or fuse, and the metal enclosure may become energized, posing a shock hazard. To ensure proper grounding, follow these guidelines. 1. Install a grounding electrode system that meets the requirements of the electrical code. 2. Connect all non-current carrying metal parts of electrical equipment to the grounding electrode system. 3. Use properly sized grounding conductors. 4. Make sure all grounding connections are clean and tight. 5. Test the grounding system to verify that it is functioning properly. Ground fault circuit interrupters, or GFCIs, are another important safety device used in electrical systems. A GFCI is a device that detects ground faults and quickly interrupts the power to prevent electrical shock. A ground fault occurs when current leaks from a hot wire to ground, such as when a person touches a live wire while standing on a wet surface. GFCIs work by monitoring the current flowing in the hot and neutral wires of a circuit. If there is a difference of more than 5 mA between the currents in the two wires, the GFCI will trip, cutting off the power in as little as 1/40th of a second. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor receptacles. When installing GFCIs, follow these guidelines. 1. Install GFCIs in all locations where they are required by the electrical code. 2. Test the GFCI regularly to ensure that it is functioning properly. 3. Replace any GFCI that fails to trip when tested. Surge protection is another important aspect of electrical safety. Surges are sudden increases in voltage that can damage electronic equipment. Surges can be caused by lightning strikes, power outages, or the switching of electrical loads. Surge protectors work by diverting excess voltage away from electronic equipment and into the grounding system. There are two types of surge protectors: whole house surge protectors and point-of-view surge protectors. Whole house surge protectors are installed at the main electrical panel and protect the entire house from surges. Point-of-view surge protectors are plugged into individual receptacles and protect specific electronic devices. When selecting surge protectors, consider these factors. 1. The surge current rating, which indicates the maximum amount of current that the surge protector can handle. 2. The clamping voltage, which indicates the voltage at which the surge protector will begin to divert excess voltage. 3. The response time, which indicates how quickly the surge protector will respond to a surge. 4. The UL listing, which indicates that the surge protector has been tested and certified by underwriters' laboratories. Electrical codes also address the installation of arc fault circuit interrupters, or FSIs. An FSI is a device that detects arc faults and quickly interrupts the power to prevent electrical fires. Arc faults are dangerous electrical conditions that can occur when wires become damaged or loose, creating a spark that can ignite nearby combustible materials. FSIs work by monitoring the electrical waveform for patterns that are characteristic of arc faults. When an arc fault is detected, the FSI will trip, cutting off the power and preventing a fire. FSIs are required in many locations throughout the home, including bedrooms, living rooms, and dining rooms. When installing FSIs, follow these guidelines. 1. Install a size in all locations where they are required by the electrical code. 2. Test the FSI regularly to ensure that it is functioning properly. 3. Replace any FSI that fails to trip when tested. Finally, remember that electrical work can be dangerous. Always follow proper safety procedures when working with electrical wiring. If you are not comfortable working with electrical wiring, consult a qualified electrician. Always to energize the circuit before working on it. This means turning off the breaker that supplies power to the circuit. Verify that the circuit is de-energized by using a voltage tester. Wear appropriate personal protective equipment such as gloves and safety glasses. Use insulated tools to prevent electrical shock. Never work on electrical wiring in wet or damp conditions. Be aware of your surroundings and avoid contact with any metal objects. If you are unsure about any aspect of electrical wiring, consult a qualified electrician. By following these safety precautions, you can protect yourself from electrical shock and prevent electrical fires. Electrical safety is everyone's responsibility.